My name is Adam Desta, and here I'll be presenting the Black Hole Lab for Physics 1. So the purpose of the experiment is to find the mass of a black hole and use that mass to determine the initial velocity needed for a spaceship to avoid the black hole, while also getting close enough to observe it. A brief preview of the results show that the mass found for the black hole was 1.02 times 10 to the 24th kilograms, and the initial ship velocity was negative 10 times 10 to the 7 meters per second in the x direction, and 7.5 times 10 to the 6 in the y direction. The first fundamental principle that is vital for this experiment is Newton's second law, which states that the net force is equal to the derivative of momentum over time, which is another way of saying it is equal to mass times acceleration. This is related to this experiment because the net force of the system will need to be calculated using momentum. Another important thing to review is the gravitational force, which is equal to the universal gravity constant times mass 1 times mass 2 divided by the magnitude of distance squared. Knowing all of these will be a big help when creating the computational model. Other relevant formulas include the velocity update formula, the average velocity formula, and the emission update formula, which is just a rearranged version of the average velocity formula. So in part 1 of this lab, I am determining the mass of the black hole. Here, the system is the black hole, and surroundings are just the star. The initial conditions are the mass of the star, which is 2 times 10 to the 30th kilograms, and time, which is 0 seconds. Delta T is equal to 86,400 seconds. So after changing the mass of the star and delta T to the mass and time mentioned earlier, I went ahead and began writing code to compute various things. First, I found the initial and final momentums, which are calculated by multiplying the mass of the star by the initial and final velocity respectively. Next, I calculated the star's changing velocity and momentum, which I did by simply subtracting the initial values from the final values. Then, I calculated dp over dt, which is equal to the change in momentum over change in time. F net is equal to dp over dt based on Newton's second law. After that, I calculated dp over dt parallel. P hat is equal to initial momentum over the magnitude of initial momentum. Then, I subtracted the magnitude of the final momentum by that of the initial momentum and divided the answer by delta t. dp dt parallel was found by multiplying this answer by p hat. F net parallel is equal to dp dt parallel, again because of Newton's second law. F net perpendicular was found by simply subtracting F net parallel from the overall net force. And lastly, the mass of the black hole was calculated using the formula for law of gravitation and all the found values. So for the results of this first part of the lab, the average mass of the black hole was found to be 1.02 times 10 to the 34th kilograms. F net was found to be 7.98 times 10 to the 28th newtons. F net parallel was found to be 1.05 times 10 to the 28th newtons. And F net perpendicular was found to be 7.92 times 10 to the 28 newtons. In part 2 of this experiment, the system is a spaceship and the surroundings are the black hole and planet. The initial conditions showcase simply the mass of the black hole, which is 1.02 times 10 to the 34th kilograms. For a computational model, I first calculated all the forces acting on the planet and ship and used them to find the net force for each one. The planets and ships' velocities were found using the velocity update formula, and the positions were found using the position update formulas. So the speed I found that got the ship very close to the black hole without crashing into it was negative 10 times 10 to the 7 meters per second in the x direction, and 7.5 times 10 to the 6 meters per second in the y direction. As you can see, the trajectory of the ship is slightly altered, but in the end, it successfully escapes the system. So for potential errors in this lab, I had to use trial and error in order to determine the initial velocity needed for part 2. So there are most likely better possible initial velocities that would get the ship closer to the black hole. Net force is equal to the rate of change of momentum. So each component of the net force should be equal to its respective component in the change of momentum. Doing it this way makes it easier to collect data, as the change of momentum is easier to find compared to that force, which is normally you would need to know every force being exerted on the system in order to find. If I wanted the ship to orbit the black hole rather than view it and escape, I would need to set the velocity in the x direction to negative 0.5 times 10 to the 6 meters per second and 9 times 10 to the 6 in the y direction. This image shows the ship's orbit in magenta. So in this lab, I determined the mass of the black hole and used that mass to determine the initial velocity needed to view the black hole without crashing, and also utilized the law of universal gravitation and Newton's second law all throughout the lab. Thank you.